let's start. Reintroduce. Okay, so let's start the new session, the second session on troubleshooting in mobile and cloud. So the first speaker is Khaled El-Maligi from Oracle Cloud, who is going to present Scrub, an online troubleshooting system for large-scale mission-critical applications.
Thanks, Oriana. So this work was done at Turn with my team, which is an online advertising startup. Oh. Yeah. And Turn was recently acquired by Singapore Telecom, and since then I left and I joined Oracle Cloud. And the paper was basically joint work between us and EPFL, working with Willie. So the main problem that we try to tackle is basically debugging large distributed systems. And this is a hard problem because basically the state there is large and distributed, and it's also constantly changing as time goes by. The problem is much more exacerbated if basically the system at hand is mission critical, because in this case we need to debug it and resolve the problem immediately. So we need basically to be able to do that, we need online querying capabilities of this distributed state. But on the other hand, while doing that, we need not to disrupt the system and its operations. Due to the importance of this problem, there was a lot of related work and previous work in literature about this. However, the real-time troubleshooting, while also having minimal impact on the target system, was not really a primary focus for this previous work. However, being able to do so, as I mentioned, is key for production systems. The issue with that, too, is it is in conflict with classical query optimization, because classical query optimization, the way it works is it tries to do as much work as possible closest to the data. And by definition, that means that you need to do as much work at the host system, which is basically contrary to what we need here. Hence, we need basically a new approach for query optimization to be able to tackle this problem. Without loss of generality, for this work, we will focus on online advertising systems as an example for mission-critical applications. And to give an example, I will basically present the Turn's real-time bidding platform. So it manages many millions of dollars in budgets for online campaigns. The system has constant introduction of bugs because basically there are a lot of features getting rolled out in a constant fashion due to continuous deployment. We have also many human or user errors, like setting up campaigns. So all these problems result in basically bugs with the campaigns, causing constant bleeding of money that needs to be detected and resolved immediately, basically, to stop the bleeding of money. The system runs at a very large scale, so it processes like many millions of requests per second. Each request is few kilobytes, and it runs across many data centers across the globe. As a result, we have data coming in like in many petabytes per day. And to log this data, it's basically prohibitively expensive. Like to do like post-mortem, the classical way to log all this data to be able to look at it afterwards is basically prohibitively expensive. Further, since these ads need to be shown basically on the web page, it has a very strict SLA of 100 milliseconds, including the wide area network latency. So the outline of the rest of this talk, I will first give some background about online advertising. Then I'm going to go through a case study showing the effectiveness and strength of Scrub. Then I will present Scrub, and then I will present an evaluation, and then finally I will conclude my talk. So to give a very simple example of an online campaign, say like the campaign will have an ID. advertiser here like is Pampers, and then it has like some targeting criteria, targeting women who just had a newborn. Their age is between like 18 and 40 years old, living in California, and the budget for this campaign is $1,000, and the goal for this campaign is to get 32,000 clicks. And then that's the creative, which is basically the ad or the image that we want to show to the users that match this criteria. So the ecosystem, the bidding ecosystem, we have basically Alice, who is a user, and then we have a bunch of publishers, for example, CNN. So Alice, say, visits CNN, then the publishers go through an ad exchange or a set of ad exchanges. The ad exchanges, basically, they meet the demand with the supply. So on the other side, there are demand-side platforms. Turn is an example of them. They are the ones providing, basically, ads. So the exchange goes to all the demand-side platform partners, telling it, okay, like I have Alice as a user. What kind of ads do you want to show? Turn, for example, then it looks at Alice. It goes through the list of campaigns Alice is candidate for, and then it runs an internal auction. Then the campaign 1, 2, 3, 4, 5 wins. Then all the DSPs go back to the exchange with their bids. The exchange actually does an auction. Then the winning ad gets to show to show the ad to Alice. And all this happens basically like in a blink of an eye. Like whenever you click on a page, all this happens. And the creative gets basically shown to Alice. Finally, Turn like gets an event with all this information, and then it logs it for further analytics later. So to further motivate the need for a system like Scrub, so I'm going to give a real production case study. So one problem that we face is basically ad spam for advertiser. Like so in one data center, like we're noticing unusual activities of bids coming at us. And we basically wanted to run this query, which basically groups the user and counts the number of bid requests I'm getting from each user. And we want to run this in one data center where we're seeing this issue. And we want to run this as soon as possible to get to the bottom of the problem as soon as possible. So with some post-processing, we're able to produce this visualization. And basically on the x-axis, you see the time in seconds, which is basically a time series starting from time 0 where we started running the query. The y-axis is the number of bid requests received. It's in log scale. The blue dots basically are showing groups of users with the same number of bid requests. So at the very bottom, like you see, users receiving a 1 request and 2 and 4 and so on. The size of the dot is proportional to the number of users in this group. And as you can see, for the most part, like as far as the blue dots are concerned, it's more or less consistent with normal human behavior, because like at each tick, a user will get few, we'll see basically few ads, and hence will result in few bid requests. However, what's most notable is basically the red triangles and the dark blue crosses on the top. So the red ones, it's basically one user, and it's consistently producing something in the order of like 100 bid requests every time slot, which is like every 10 seconds. And then basically the blue crosses, those are like in the thousands. And those obviously are not human, like that's not consistent with human behavior. So the conclusion was those were bots, and basically we shut them down. But the thing is, this needed to be detected instantaneously to be able to shut it immediately, because otherwise like we're effectively bleeding money. Without a system like Scrub, there was no way to be able to catch this problem in such a way. So now I'm going to talk about Scrub. So Scrub is a real-time troubleshooting tool for large systems with strict SLAs. It queries large distributed state to produce real-time results. It has negligible overhead on the target system, and it is horizontally scalable, so it can handle as much load as needed by adding basically more machines. So let's see at a high level, like basically how a query gets executed using Scrub. So a user submits a query to the Scrub server. For example, this query, which is doing a select and grouping for a particular servers in a particular data center. the Scrub server breaks down the query into different operators. Some operators gets pushed to run at the host, which are basically the selection and the projection, and then the grouping gets sent to a Scrub Central, which is a centralized service that does basically the aggregation and the joins. After the query has been installed at the host, then subsequent events that pass the filters get passed to the central processing unit where the final aggregation is done, and finally the query result is saved there. So in more details, the system architecture goes as follows. So we use Zookeeper basically for asynchronous, reliable message and object passing between different entities because the system spans basically it's across the world. We use Kafka as our persistent and reliable message queue for passing events from the hosts to our central processing unit. And we use HBase for our persistent storage. So now I will talk about special, like the key contributions that this work has that basically strays from the conventional wisdom or the previous work. So for data collection, what I mean by data collection is collecting the data at the hosts. We stray from what previous work has done, which is relying on dynamic instrumentation to collect data at the host. What dynamic instrumentation does, it relies on facility in the languages or programming languages to basically deploy and at runtime arbitrary instrumentations. But this was inadequate for our use case because two things. First, the performance was unacceptable for our workload because, for example, in Java, to be able to do this one dynamic instrumentation, it costs like 100 milliseconds of freezing the world as far as Java is concerned. So this was unacceptable, as well as security issues because you can, allowing arbitrary code to be injected then in a production system, then you can have malicious code or buggy code be injected and that can compromise the system. So this was not adequate. Instead, we basically had our system to be integrated with the Scrub library. And the downside of not using dynamic instrumentation, we needed to change the actual host code. But the changes were minimal. Like you just needed to call into our library whenever you want to expose an event. You just call into the library, and the event becomes visible to our Scrub system. Then the application using this, the applications emit the events of interest. And the emission, all what that means is it just gets enqueued into a drop-tailed non-blocking queue. And then the application thread can continue execution as normal. Hence, there is very little disruption to the application code. Then there is a thread pool, Scrub thread pool, that basically dequeues events from this queue. And it then evaluates the filters and projections and then pushes the events that pass these filters downstream to the central processing unit. The Scrub thread pool runs at a low priority, and hence under heavy load, the Scrub threads yield the CPU to the application threads, and events can get dropped. But that's a design choice we made so that we don't want to compromise the application performance or operations. And in practice, only under like 0.1% drop rate was experienced, and that can even be further reduced if need be by increasing the queue length to absorb like bigger spikes. Another thing we've done is as I said, like we strayed from the conventional query processing strategy, which is basically doing a lot of the query processing away from basically where the data is. So we push a lot of data to the central processing unit. The central processing unit is horizontally scalable, so you can add more hosts. It relies on streaming operations, so the joins and aggregations are done in streaming fashion over windows, basically time windows. And the output comes out as a time series per query. It's sorted on HBase as basically a time series that can be easily queried. The join operation also is different than what's in the literature. We use streaming equi-join. Typical streaming equi-joins, you just join two large streams together, you chop the streams into windows and then join the events within each window. Here, it's a little bit different because we have two kinds of windows. So there are the standard standard streaming windows for aggregation, but for joins, each request has its own window, and the window is basically starts from the first time we see the event for this particular request. And it's basically governed by the request lifetime. The window there is governed by the request lifetime. So one key contribution we have in this work is we're basically trading accuracy for performance. So the key use case we have is outlier detection, as we've seen in the spam detection case, or to basically get directional guidance. So in the directional guidance case, we just need to see that the result is consistent with what we know. And hence, complete accuracy is not required. Examples of these trading accuracy is dropping events and sampling. And in practice, as I said, we have very little drop rate. The overhead on the target system in practice was very minimal. It's just 2.5% of CPU usage for the scrub threads, and under 1% increase in request latency. The throughput of Scrub Central was also pretty good, like over 400K tuples per second. And hence a small cluster can handle the multi-million requests per second workload from turn. To conclude, Scrub is a troubleshooting tool for large distributed applications. It's real-time and it's scalable and adds negligible overhead to the target system, which is key for production environments. It's been used at turn for 2 years and handles millions of requests per second. It quickly resolved many numerous complex problems, many of which are case studies in the paper. And that concludes my talk, and thanks, and ready to take questions.
Questions? I can ask a question. So I guess that when you started this work, you probably started by using some state-of-the-art tools. And what was really the feature or the group of features that kind of made you realize that that wasn't sufficient? And so you went into implementing Scrub.
So in practice, the state-of-the-art is basically just logging. So you just log whatever information you need, you just log it, and then after this, do post-processing. The problem with that is the scale is, so there are two problems. One problem is you don't really know what to log a priori, because if you log everything, it's just tremendous amount of, so you use your best guess to log what's needed, but then oftentimes you're wrong. This piece of information is not logged, and then you don't really know how to resolve the problem. And even with logging and using this best effort, the amount of data is just tremendous. So it was just inadequate, and without the system, resolution time was, and we are a startup, we're not like a research lab or university, so we're not doing this just for the intellectual exercise. This was a really needed thing. So the resolution time was just too long, and then it resulted in a lot of loss of money and a lot of problems. So we had to do something like this. The work that we've seen in literature before was inadequate because of the things that I mentioned. So all these things basically pushed us to build something like this.
Any other questions? No? So let's thank the speaker.
Yep.
Our next speaker is Marco Brocanelli from Ohio State University, and he's going to present Hang Doctor, runtime detection and diagnosis of soft hangs for smartphone apps.
Thank you. I'm a PhD student at Ohio State University, and we're going to talk about soft hang bugs and how to detect them on mobile apps. So smartphones are primarily user-oriented devices. So they are considered to be good if they are responsive to user actions. This means that we desire that every user action has a response time shorter than the minimum human perceivable delay, which several studies estimated to be 100 milliseconds. So generally users of smartphones are very impatient. So if they see some sluggishness or problem and delay with the user actions, then they may get impatient and eventually kill the app or give poor user ratings. So one of the major causes of these responsiveness problems are programming issues, such as soft end bugs, which are our focus. Soft end bugs basically cause soft hangs, so they are limited but perceivable delays. So eventually the app will respond, will give a visual feedback. It's just that it takes a long time to do it. So let me give you some background on soft end bugs. So in mobile apps, usually you have a lot of threads, but only one thread called the main thread or UI thread. It's designed to receive and execute user actions, and then eventually also to do updates on the user interface. So basically, this means that every long operation should be executed off the main thread to avoid blocking it and generating soft hangs. And here is the definition of the soft hang. Basically, a soft hang bug is nothing but a long operation executed on the main thread of the app, like in this example. And as one can imagine, we can fix a soft hang bug by just moving this long operation on a background thread so that the main thread can be more responsive to the user action. However, one thing to note is that we cannot just move everything off the main thread, so there are some APIs called UI APIs that must be executed on the main thread because those are needed to update the user interface. So basically UI APIs are not soft hang bugs. And as a result, developers need our help to find those soft hang bugs. Previous work in soft hang bugs detection primarily works offline. This is desired because they could detect soft hang bugs before the market release of the app. So the way it works is that they just scan the source code of the app and look for some well-known heavy operations, such as, for example, database operations, bitmap code, or network operations. Now, the problem of these existing algorithms is that they have to rely on a sort of database of what is known to be heavy. So they are going to miss eventually new or unknown heavy APIs. Also, if those heavy APIs are nested inside third-party libraries and then the source code cannot be, for some reason, cannot be accessed by the offline tool, they're missed as well. And generally, they don't check self-developed lengthy operations such as long loops. So as a result, even after applying these offline tools, soft hangs can be missed and manifest at runtime. So at runtime, the main approach is called timeout-based, and basically it detects any soft hangs that is longer than a certain timeout. For example, Android currently set this timeout to 5 seconds. And this long timeout actually causes many false negatives because soft hangs manifest with a response time longer than 100 milliseconds. However, if you just decrease the timeout to 100 milliseconds, we would get a lot of false positives because of some soft hangs caused by the UI operations. So the main challenge at runtime is to actually efficiently detect, understand when a soft hang is caused by a soft hang bug, and then eventually understand what is the root cause of it, and when instead it's just a UI operation. So to solve all of these shortcomings of existing work, we propose HangDoctor, which is a runtime solution to detect soft hang bugs. And in order to ensure high detection quality and low overhead, HangDoctor runs for every user actions and is designed as a two-phase algorithm. So basically, the first phase, it is a lightweight soft hang bug symptom checker where actually analyzes the user action execution and try to understand just if a detected soft hang is just caused by a UI API or a soft hang bug. If the first phase detects as most probably a soft hang is caused by a soft hang, but then we analyze that user action with the diagnoser, which is the phase tube, and which basically does some stack trace analysis to understand what is the root cause of a soft hang. If indeed find a soft hang bug, then it reports this bug to the developer, and eventually it adds this new unknown API to the database of well-known APIs, so we can improve the offline detection performance. So let me give some details now on the two phases. So as I said, the first phase actually is just like a filter that we try to understand if a soft hang is caused by a UI operation or a soft hang bug. And so in order to do this distinction, we actually look for what are soft hang bug symptoms, just like when we are trying to find out if we are sick. So we have to define these symptoms, and we have decided to use performance event counters. So why do we want to use performance event counters in the first place? This is for three main reasons. So the first thing is that they provide a lot of low-level information on the app performance. And then there are many different hardware and software events for example, like many smartphones, they have hundreds of different events, such as, for example, the number of instructions of a certain thread, the cache misses, the context switches, and so on. And the third reason is, it's the most important, is that they have a relatively low overhead, which makes them suitable for the first phase that has to be lightweight. However, we cannot just go ahead and use all the performance counters to do the filtering for two reasons. First, there are only a limited number of registers available for the counting. And second, actually some of the events may not be very good to distinguish UI APIs from soft hang bugs. So our target actually now is to find few counters that can give us a high detection quality. And we do this by executing an offline correlation analysis between the performance counters and the soft hangs. To do this, we first built a training set of 10 well-known soft hang bugs and several other UI APIs. Then the idea is to profile the execution of each one of these samples in the training set and then understand what are the symptoms. So one of the problems we had to solve is which threads of the app we want to monitor. So of course we are going to monitor the main thread because it's where the bug is, so we should monitor it. Now actually apps have also a render thread. Now the render thread receives actually jobs of UI updates from the main thread, and then it handles all the communications with the GPU to display every frame of the animation eventually. So what we actually observe that helps in the correlation is that when a soft hang is caused by some UI APIs, usually the main thread sends a lot of job to the render thread. So we can say that this is a kind of a symptom of a UI API. However, when the main thread has a soft hang caused by a soft hang bug, then actually the main thread does not produce so many jobs for the render thread, which is normal because soft hang bugs don't produce much result to update the UI. So actually, this is the main observation that helps us to get a good correlation of the performance event with the cause of the soft hang. And in practice, here are the results of the analysis. And basically, a higher correlation coefficient indicates a better ability of the event to distinguish UI APIs from soft hang bugs. So basically, now that we have a sorted table of which events are better to use, now we have to decide which ones to use. So in order to do so, we design a selection strategy of the events. And basically what we do is that we start from the most correlated event, in this case the context switch counter, and then we find the threshold that minimizes the number of false positives and false negatives in the training set. So here we show like the context switch difference, which is the difference between the context switches of main thread minus render thread. So basically, one candidate good threshold is, for example, we can observe here that 90% of the handbugs in the training set had a positive difference, whereas 90% of the UIPIs have a negative difference. And this is mainly because what we said before with intuition, that usually during hangbugs, the main thread does not produce much work for the render thread. So eventually, if with the selected threshold we get some false negatives, like for example in this case, then we add another counter and we find another threshold for this counter, and then we do this for until we can detect all the bugs with at least one of the counters. So doing so, we end up selecting 3 event counters, and which are the context switches, task clock, and the page fault. And we get an 81% accuracy without any false negatives. So then at runtime, basically every time that we detect a soft tank, we check basically the event counters. And if at least one of them is higher than the selected threshold, then we transition this user action to the second phase diagnoser for a deeper analysis. Otherwise, we don't do anything to limit the overhead. So in the diagnoser, basically the main job of the diagnoser is to first understand what is the root cause of a soft tank, and then understand if this soft tank if this root cause is a soft tank bug or a UIPI. So basically what we collect with the diagnoser is this. So we monitor the response time of an executing action, and then if the timeout of 100 milliseconds is exceeded, then we start collecting stack traces periodically until the end of the soft tank. Then we do the trace analysis. So one thing to note is that why do we do it periodically? Why do we periodically collect stack traces? Well, actually we do this because we observe that a long operation executing during the user action, then it would appear in most of the stack traces collected, because the main thread is stuck doing some long running operation. So this is why actually during the first step of the analysis, where we want to determine what is the root cause, actually we go through the stack traces collected, and then we find what is the the operation that appeared the most across the stack traces. And then eventually we can get also the file name and the code line number of that root operation. Then in the second step of the analysis, we want to determine if this is a soft tank bug UIPI, and we basically find UIPIs by reading the class name of the root operation. If it's a classic class of like view or widget that I use for updating the UI, then we deem this soft tank as a false positive. Otherwise, we give the soft tank back to the developer. So we have implemented Hang Doctor and deployed it on the devices of 20 users. And we have tested about 114 real apps and on the devices. And we actually found 34 new soft tank bugs that were previously unknown to the developers. And then we have used a state-of-the-art offline detection tool to see which ones of these bugs could have been detected. And we actually get that 68% of the bugs were missed by the offline tool, simply because they were caused by previously unknown heavy APIs. And then actually 8% of the bugs that could have been detected offline, maybe because of some file IO or database, they were actually nested in third-party libraries. So eventually the offline tool could detect those only if the source code of those libraries was available. Of 62% of the bugs have already been confirmed by the developers. In many cases, they released a new version of the application which was more responsive. And for the remaining 38%, we actually just manually confirmed that it was indeed a soft tank bug by fixing it. So just as one of the results, we want to show the validation of the correlation analysis for the first phase. So in order to do the validation, we test the first phase, the filter, with a validation set of 23 bugs that were previously missed by the offline algorithms. So they are not included in the training set. And so here on top, we actually see an execution of canine mail when you want to open an email. And there was a soft tank in this user action. And basically, the first phase actually reads the counters of both main thread and render thread and finds a positive difference, which was one of the symptoms of soft time bugs. So it correctly detected that this one was indeed caused by soft time bug, and then it finds it using the diagnoser what is exactly the root cause. So this one is a graph to summarize basically this, the first phase over the 23 different bugs in the validation set, and basically each color corresponds to one of the 3 counters and which one of them actually can detect the bug. And basically what we get is that all the soft time bugs, all the 23 soft time bugs in the validation set can be correctly detected, and compared to the timeout-based baseline, we get a 90% lower false positives, which lead to a 63% lower resource usage overhead. In the paper, there are many more results, so I invite you to go look for them. So in conclusions, we have proposed HankDoctor, which is a runtime detection and diagnosis tool for soft time bugs in mobile apps. And we have designed it as a two-phase algorithm to ensure high quality performance and low overhead. And we based the HankDoctor on performance counters and used a correlation analysis of performance events with soft tanks. And we have tested this with real-world apps and got good results. This concludes my presentation. Thanks a lot.
Questions?
Hi, can you hear me? Very nice talk. So I have a quick question. You show that the page fault has correlation with the bug manifest, right? Do you have any insights? Why?
Page 4, do you mean?
So you have 3 good features.
Oh, yeah. You mean this one?
Right, you show context switch,
Yeah.
and page fault, and one more thing. So why page fault has something to do with hung?
What I can tell you is that actually we studied this, why we have exactly these events as the top correlated. So the reason is that compared to other events, such as, for example, the number of instructions, these events are actually, they increase more because of OS decisions rather than the particular source code of the bug. So that is why basically the best event is basically the one that can generalize some symptoms of groups of ham bugs and groups of like UI APIs, right? So they all have different source codes, but so the filtering can be better if they're not very dependent on the source code. So that's why maybe the context switches or the task clock or page fault, they all depends on more on the OS decisions rather than the bug.
Okay, thank you.
So I'm interested in whether this scales down to doing audio latency stuff. So, because visually you have 100 milliseconds, but for audio you have about 10.
Yeah.
What are the limitations on how far you could scale this down and say, well, I want to detect could I do 10 milliseconds? Could I do 25?
Well, yeah, I mean, of course it's going to be more problematic because then if you want to, so one of the problems we had to decide is how to detect what is the root cause, right? So we are talking about detecting exactly what is the code line to tell the developer you have to move this off the main thread. So you can do this in 2 ways. Either you do some code injection and you maybe log every execution of the APIs in the code, or you just collect the stack traces. So we decided to go with the stack traces because are more can be managed when you dump them, so you can decrease the overhead. But if the timeout is very short, maybe we could get a slightly much higher overhead because you have to do it in a very short period of time. Then there are always delays, and you may. I would say that the overhead would be more of a problem because you have to make sure that you collect the stack traces within a very short period of time.
Christopher Stewart, Ohio State. I'm just a follow-up to that. It seems like if you were trying to detect at millisecond scale, or the alternative, if the number of threads blew up, for instance, if you were doing future apps that are edge-based, that have multiple threads, not just main and render, it seems like you would have a hard time with context switches as your correlation, as your metric, because you need to get so many in order to have a decent confidence that this is really reflective. So I'm wondering if you've done any analysis where you've reduced the timing that you do for collecting context switches. Like, what happens if you try to get this to detect with 1 millisecond?
So we get into
or
some
half a
troubles
millisecond?
actually, yeah, because so I just need to find the backup slide for that. Yeah, this one. So we said basically, let's see if I understood the question. Why do we have to wait for the end of the action when we can just collect some few samples at the beginning and we base the filtering on those? So actually, we decided not to do that for the simple reason that at the beginning, the main thread actually does some job before he has to calculate where is the position you have of the button. So then it sends that to the render thread. So basically, if you see at the beginning of the execution, we would get like the main thread, this is for the context switches, right? We would get that the main thread usually has a more higher workload than the render thread. So this would lead to more false positives. So if we have a much shorter timeout, then eventually we could rerun the correlation analysis offline and then update the events used. But for
Let's thank the speaker. So our next speaker is Chashin Lee from NUDT and University of Chicago, and he's going to present PCatch, automatically detecting performance cascading bugs in cloud systems.
Yeah, good morning, everyone. Thank you for coming here. I will talk about the paper, PCatch, automatically detecting performance cascading bugs in cloud system. I'm a PhD student from National University of Defense Technology in China, and this work was done with people at University of Chicago and North Carolina State University during my visit to Chicago. And particularly many thanks to Professor Sanlu and her group for their help. And at present, distributed systems such as cloud storage, data parallel, computer frameworks, and synchronization services have become a dominant backbone for modern clouds. And given the inherent distributed and redundant nature of cloud systems, people usually expect high scalability and performance isolation. However, a type of poor software design could violate both goals at once, and we refer to this kind of software design problem as performance cascading bugs, short as PC bugs. And so, what are PC bugs? That is the slowdown of one job unexpectedly propagates to affect other jobs. And here is a real-world PC bugs example in MapReduce. And client submit a job to job tracker, and job tracker begins to assign and run tasks on task tracker. Here are 4 threads. Third one, because third one does time-consuming work. That is copy a big file by holding a log 1, and the third 2 holds log 2 and has to wait for log 1 to release. And third 3, similarly, third 3 holds log 3 and waits for log 2. And thread 4 waits for log 3 and cannot send habit to job tracker in time. And consequently, the task tracker node will be killed by MapReduce, and all of jobs running on it will be re-executed and delayed. As we can see, PC bugs are kind of global performance problems, and actually, PC bug consists of a triplet LCS, and L is a workload sensitive source, which is a non-scalable code region like the loop taking a long time, and C is a cascading chain, and S is a time-sensitive sink. And how to detect PC bugs? There are 3 challenges. There is PC bugs are workload sensitive and non-deterministic and have global symptoms. And so can we predict PC bugs by only analyzing small workloads? And can we pinpoint performance cascading chains and identify the slowdown root causes? There are lots of previous work detecting performance problems in single machine systems. However, there is still no effective solutions for detecting PC bugs in cloud systems. This is our contribution. I will talk about them later in detail. This is an overview of PCatch. PCatch is designed to predict PC bugs that can affect the performance of any specified user job or system routine by only observing correct runs under small-scale workloads. And for each concerned time-sensitive sink specified by users, PCatch will conduct the following three steps of analysis. There is cascading analysis and job origin analysis and loop scalability analysis. And finally, catch potential PC bugs for users. And the whole process is hybrid static and dynamic analysis. And next, I will talk about the 3 parts of PCatch one by one. Cascading analysis. Its goal is to conduct a performance dependency analysis. That is to identify the performance cascading chain from source L to sink S. And for doing that analysis, we build a performance cascading model, modeling 2 types of relationships that could contribute to performance cascading. We first model causality relationships, also named must happens before, and we introduced distributed happens before analysis to conduct our must happens before analysis. For example, in HBase, for an operation O1, we have to analyze a variety of relationships such as thread creation and the RPC call, or enqueue, or handle an event, custom update and custom push, and so on operations to figure out that O1 must happen before O2. And if there does not exist, O1 must happen before O2, and O2 must happen before O1, then we will consider O1 and O2 are concurrent. And we name model resource contention relationship, also named may happens before. For logs, for example, there are 2 critical sections in 2 threads. And if they require the same log L and log 1 and log 2 are concurrent, then any operations inside this critical section will have a may happen before relationship to log 2. Similarly, and in addition to log-based resource contention, we also consider event or RPC handling contention. For example, here there are 3 event or RPC handlers, handler 1, 2, 3, in 2 threads of the same thread pool. Then if start of handler 1 and the start of handler 2 are concurrent, then every operations inside the handler 1 may happen before the start of handler 2. Similarly. And after that, we try to compose master happens before and the main happens before. An example in Cassandra. This is source and this is sink, and this is a cascading chain from source to sink, consisting of 5 segments. And the first one segment is about may happens before, and the last 4 segments about must happens before. And the key idea of our cascading analysis algorithm is simple. It is a reverse process. That is starting from a sink and ending up with a source. And in each step, we need to conduct both must happens before and may happens before analysis. And the job origin analysis, its goal is to differentiate global performance cascading problems from local ones. And that is to identify, that is to check whether the 2 code regions, sense and source and sink, belong to the same job or not. If not, it is actually a global problem. And there are 2 types of jobs. User jobs triggered by calling applications APIs from users, and system routines triggered by background systems of background threads of systems. And we conduct dynamic tracking analysis in the happens before graph. For example, for the source, let's file copy loop. We check backward along the causality edges and finally find that it is from client's submission. For this user job, we consider process ID and force message ID as its job ID. And for system routine, we consider process ID and background thread ID as job ID. And for loop scalability analysis, its goal is to identify potential slowdown sources. That is to identify loops satisfying 2 conditions. The first one is each iteration of a loop is time consuming, and the second one is loop is non-scalable. That means the number of loop iterations, that's loop count, does not have a constant upper bound and can potentially increase together with the workload. And the fourth condition is easy to figure out, and we will focus on how to identify non-scalable loops. We abstract the 3 patterns for non-scalable loops. Type 1 is loss loops with a loop invariant index. For example, the loop count of the loop is determined by the Boolean variable rjob.locking, which is updated by other threads. So we consider this kind of synchronization loops as potential non-scalable loops. And type 2 is loss loops with a workload sensitive index. The loop count is determined by the variable byte rate. However, the value of byte rate is updated by I/O operations inside the loop body. We also consider this as potential non-scalable loops. And type 3 is those loops with workload-sensitive bound. For example, the loop count is determined by the size of the collection variable to add. We will then do backward slicing to confirm if the loop count is workload sensitive or not. And now is evaluation. We evaluate our tool in 4 widely used open source distributed systems, including Cassandra, HBase, HDFs, and MapReduce. And based on 8 bugs that we were aware of, we use common small-scale workloads without special timing requirements, like the word count for MapReduce and the write file for HDFs. And we specify important system routine like heartbeat and main tasks within a client request as things like map task for MapReduce and region assignment for HBase. Our tool reports 33 PC bugs with 22 true bugs and 11 false positives. In these 22 true bugs, 15 we were aware of, and 7 are new bugs we find. And to confirm the PC bugs reported by our tool, we trigger the name by using large-scale workloads, and manually coordinate the workload timing. The columns here shows the workload size we used during our detection run and triggering run. And for example, in HDFS 2379, we use 3-block data in our detection run, and the sync time is less than 1 second, and we used over 800,000 block data to trigger the bug, and the sync time become 19 seconds. Now, conclusions, there are 2 things, PC bugs and P-catch. That's all, thank you.
Questions? So you show us how many bugs you found, but how many you didn't find?
For our totally 8 benchmarks, we found we detected all of benchmark bugs, and and also we have false positives here. Yeah.
Sure, but these were bugs that weren't bugs, but
Yeah.
what about false negatives?
Because
I guess it's hard to compute, right?
Yeah, it's difficult
You have to do manually.
Yeah. So, but in our experiment, we found out of benchmark bugs, so there is no negative, positive. Yeah.
Okay. Any other questions? No? So let's thank the speaker once more. Thanks. You can put it on top. Our next speaker is Jonathan Mays from Brown University, and he's going to present universal context propagation for distributed system instrumentation.
All right. All right, hello everyone. I am Jonathan Mace. My advisor at Brown is Rodrigo Fonseca, and today I will be talking to you about context propagation in distributed systems. So context propagation is an important component of many tools that monitor and enforce distributed system behaviors. But context propagation requires significant time commitment from developers who have to go and instrument their system's source code to propagate contexts. So in this work, we generalize and abstract context propagation so that it can be shared and reused by different tools. This drastically reduces the effort required to deploy new cross-component tools in distributed systems. At the heart of our solution are baggage contexts, a general-purpose serialization format that provides a key property. And that's the ability to merge two serialized context instances into one without having to interpret the serialized data. This property is what enables us to decouple context propagation from the tools that use it. So to start the talk, I'm going to take a step back and just give you a quick look at the broader setting. So the distributed systems that we're all used to are by their nature quite complicated. So individual systems internally comprise many interoperating processes, and at the same time, we design our systems to compose and interoperate with one another. So ultimately, a high-level execution from a user, such as a single API call, a processing pipeline, or a data analytics job, is going to involve multiple processes, components, and systems. It'll have multiple hops over the network, and it'll do concurrent work across multiple machines. Many problems can arise in this setting, and in the past decade or so, researchers have proposed various tools and techniques for tackling them. In this work, we focus on a particular class of tools that we term cross-cutting tools. These are runtime tools for distributed systems that coordinate across the boundaries between components. And they do this using context propagation. So I'll show you an example of how context propagation works by illustrating a distributed tracing tool, which falls into this category of cross-cutting tools. So you might already be familiar with distributed tracing tools like Xtrace, Dapper, or OpenTracing. The goal is to combine logging statements, or events, across all system components. To do this, system developers will modify their system source code at various points to emit logging statements. At runtime, when an execution reaches these points, they will emit events that are aggregated by the tool's backends. And this is done across all system components for the end-to-end execution. I think this has started to die. All right, so these events, this gives us the events. And from here, we need two further things in order to construct a trace. First of all, there could be concurrent but unrelated executions, and we want to separate the events related to each individual execution. Then second, we want the order and causality between events because of internal concurrency within executions. To get these things, we record additional information at runtime, and this is where context propagation comes into play. At the start of an execution, the tool will assign it a unique execution ID. This ID must then be propagated alongside the execution wherever it goes through all system components. That way, the tool can then annotate every logging statement with the execution ID. And then the backend can distinguish between events which belong to each execution. To then get the causality between events, we need to go a step further. Whenever an event is generated, it's assigned a unique event ID. Then, in addition to propagating the execution ID, we'll also propagate the ID of the most recently seen event, or predecessor as it's labeled here. We update this predecessor whenever we generate a new event. Concurrent branches of execution can therefore have different predecessors, as they're essentially independent from one another. If concurrent branches at some point rejoin, then they'll retain both predecessor IDs, as shown here. So using this, each event can explicitly record its immediate predecessors, and then using these predecessor IDs, the backend can construct the relationships and ordering of events. Now that was a really quick description of distributed tracing and how it uses context propagation. But this example shows how propagating contexts with executions is useful for communicating information across components. Beyond distributed tracing, there are a wide variety of tools that do different tasks and propagate different kinds of metadata. So for example, there are tools for scheduling, latency, and resource management. They propagate things like tenant IDs, latency measurements, and critical path estimates. Instead of logging events, they use this data at runtime to coordinate throttling and scheduling decisions. Other tools for metrics and monitoring will dynamically propagate tags, identifiers, and tuples that they use for grouping and filtering metrics across components. There are many other use cases besides these, and in general, different tools will propagate different things, ranging from simple static IDs to more elaborate dynamic data types that get updated during the execution. Now, despite the differences between tools, they all share one thing in common, and that is the need to do system-level instrumentation. Because actually propagating contexts requires developers to go and modify their system's source code at all execution boundaries. So for example, contexts have to be explicitly retrieved from RPC headers, then stored in, say, a thread local variable. If new threads are created, contexts have to be copied for the new thread. They have to be serialized and included in RPC headers. They need to be included through any queues, continuations, event callbacks, asynchronous communication, and so on. In all, instrumentation entails pervasive modifications to all system components to make sure that contexts are propagated with everything an execution does. And it's required for all components, otherwise the context could be dropped partway through execution. All cross-cutting tools require instrumentation for propagating contexts, and that requires significant time and energy from developers, and is easily regarded as the biggest cost in deploying cross-component tools. Moreover, all cross-cutting tools to date entangle context propagation with other elements of the tool, which inevitably leads to instrumentation that cannot be reused or shared with other tools. So to go and deploy a second tool will mean revisiting all of the instrumentation for context propagation. And that's a huge obstacle. So our contribution in this work is to generalize the context propagation piece of these tools. That way, instrumentation for context propagation is only done once, in a general way, and thereafter cross-cutting tools can share and reuse instrumentation to propagate whatever data they like. Doing this requires a flexible intermediate data format, and that's the role of baggage contexts. They give us a concrete underlying implementation to bind our systems to at development time, and they're carefully designed so that they can represent any data types that might be needed by cross-cutting tools at runtime. Those internal details of baggage contexts are not something that we would want to expose to cross-cutting tools directly. Instead, we provide an interface definition language called BDL, or Baggage Definition Language, for specifying the data types that we want to use in our cross-cutting tools. The BDL compiler produces the code for interacting with baggage contexts, hiding the underlying data format. Overall, this forms a layered architecture that we call the tracing plane, that separates the concerns of cross-cutting tools from system-level instrumentation. This separation has a huge benefit. Previously, someone deploying a cross-cutting tool would have to juggle several skill sets that have to know everything from the underlying system all the way up to all the elements of the cross-cutting tool. By separating these things, we also separate the skill sets needed for each task, providing a lower barrier to entry for deployment. So I'll describe some of these layers in more detail, starting with the system-level instrumentation. So instrumentation for context propagation is encapsulated in what we call the transit layer. System developers instrument their systems to propagate opaque baggage context objects using an API of 5 propagation operations. Of these, serialize and deserialize simply convert baggage contexts to and from a wire format. Branch is used to derive new context instances when executions split into concurrent branches, since each execution branch requires its own context copy. Merge is used to combine two incoming baggage contexts into one whenever concurrent execution branches rejoin. And finally, trim is used to impose a size constraint, but I'm not going to get into this in the talk. So that's all we need for instrumenting systems. All of these operations treat baggage contexts as opaque objects, so that instrumentation isn't bound to the data of any particular cross-cutting tool. If we now move to the topmost layer, here cross-cutting tool developers simply specify what data types they want to be propagated for their tool using BDL. BDL specifications can use a range of different data types, including primitives, nested data structures, and more. As an example, our earlier tracing tool propagated an execution ID and a set of 0 or more predecessor IDs. So in BDL, we would specify an integer execution ID and a set of integer predecessor IDs. We give the names, types, and a positional index for the fields that we want to propagate. We can add new fields and deprecate old ones without affecting compatibility with prior versions of a tool. This looks and behaves a lot like protocol buffers, but there is a key difference that I will describe momentarily. So from a BDL specification, tool developers use the BDL compiler to generate accessor interfaces. The tool can use these to get and set variables from baggage contexts. So for example, setting the execution ID and adding a predecessor would look something like this. The intervening two layers define baggage contexts and provide the bridge from instrumentation to those elaborate data types used by cross-cutting tools. The first of these layers, that we call the atom layer, provides a concrete underlying serialization format, as well as concrete implementations for each of the 5 propagation operations. Then on top of that underlying serialization format, the baggage layer specifies encodings for BDL data types that map down onto the atom layer's serialization format. So in order to support nested data types and to multiplex cross-cutting tools, the overall representation of a baggage context ends up being a tree. The nodes of the tree are used for addressing, and the values of data types live at the leaves. We'll come back to this in just a second, as I'm going to go a little bit further into the details of these inner layers. But I won't go all the way to talking about the bits and bytes of the actual serialization format. For all of those gory details, I'll let you take a look at the paper. So recall the 5 operations that system developers use to instrument their systems. Of these, serializing and deserializing are trivial, and branching simply involves duplicating the context, 1 copy for each branch. The operation that makes everything tricky is merging. Merging significantly impacts our design at every level. Concretely, all BDL data types need well-defined merge semantics, because we need to know how to correctly merge 2 instances of a data type whenever 2 branches of an execution join. We want to make sure that we combine them in a way that makes sense for the data type. For example, our set of predecessor IDs has a somewhat natural merge operation of a set union. If there are 2 different baggage context instances that have different values for a predecessor ID, then what we want is to take the set union after merging. I also just mentioned that we represent baggage context instances overall as a tree. So if we had this baggage context with an execution ID and a predecessor, and we wanted to merge it with this one that just has a predecessor, the desired merge behavior of a tree will extend in a similar way. We want to match the nodes of the tree based on the node's ID and recursively merge their children. If a node only exists in one of the input baggage contexts, then we would retain that node and all of its children. When we reach a leaf, we want to merge based on the data type of that leaf. In this example, we would do the set union of predecessor IDs that we just saw. Many of the ad hoc approaches to context propagation used in existing systems today do not sufficiently handle merging and trivially fail to correctly preserve data types through mergers. So merging then also makes the design of the underlying serialization format tricky. we need a single underlying representation that can lay out that entire tree of a baggage context and support encoding of the tree and of any of the data types at the leaves of the tree. Then, with those final encoded bytes, we require a single concrete merge function that operates only on the bytes. That merge function must correctly preserve the merge semantics for the baggage context tree and all data types therein, such that when we decode it, we get the correct merged object back. In the paper, we describe a merge function that achieves this. In short, it is idempotent and order preserving, and it can correctly preserve data type specific merge semantics without having to interpret the data whatsoever. So for every single data type supported by BDL, its encoding into a baggage context can be arbitrarily merged in its encoded form. When we eventually come to decode, what we get back will reflect the correct merge of the data type at the object level. So you might ask, why go to the trouble of doing all of this in the first place? Couldn't we do some amount of interpretation of the bytes? Well, by providing a single, simple, well-founded merge function, it means the minimal requirement to be able to propagate contexts is only the atom layer. This is a very low barrier to entry. For example, implementing this in Go required less than 100 lines of code. This makes it very easy for us to support baggage propagation through many different languages and to incorporate new languages quickly. And remember, that kind of logistical issue is precisely the kind of problem faced in deploying cross-cutting tools today. So I'm only going to summarize our actual implementation and evaluation. So we implemented the tracing plane in several languages, primarily evaluating our Java and Go implementations. We presented in the paper 6 cross-cutting tools, some of them updates of existing tools, others being new tools entirely. And we deployed them across a range of distributed systems, including data analytics and microservice environments. In our evaluation, we deployed these tools side by side and showed that they can correctly propagate contexts in all of these systems. And this is done using only the generic low-level instrumentation of those 5 propagation operations. In some of these deployments, executions traversed components in different languages, demonstrating cross-language interoperability. And as a sort of final evaluation piece, we typically only add about 20% overhead compared to a static encoding of this data, so it's very efficient. So that was a whirlwind tour of baggage contexts, and if you're building a distributed system or a cross-cutting tool, we would invite you to consider using baggage contexts inside your system. And with that, I would like to thank you for your attention and invite questions.
Questions? Go.
So if a context is split into 2 concurrent branches and then later merged together, do you need to order those concurrent context branches together?
When you say order them...
Order, so basically for 2 concurrent branches in distributed systems, unless you have vector clocks or whatever, if they don't have correlations, it's very difficult to order them. So
right.
When you merge them together, do you need, so after the merge, of course they have a causal relationship, it's easy to order, but before that, so after the contexts are split and before they are merged, there's some concurrent branches. So do you need to merge them, or there are some scenarios that you actually need to merge them?
So this is dependent on whether the baggage context itself has data added to it in those concurrent branches, and whether those data types need to preserve the fact that there is no ordering between them. So some of the data types that we have do in fact enable this, but many data types don't need it, and therefore there's no reason to do that. For example, if you're propagating a set of things, you may not care whether 2 elements of that set were added concurrently or in any particular order. And this is where the sort of flexibility with data types comes in very handy, because you can go down to the simplest and most efficient data type available to you. So yes, we can handle it if we need to.
Any other question?
All right.
Let's thank the speaker.
Yeah, I'll go speak to Chris in a second.